Second speaker for this tutorial is Nicola Da Dalt. Nicola Da Dalt received the MS degree from the University of Padova, Italy in 1994 and a Ph.D. degree from RWTH Aachen, Germany in 2007, both in electrical engineering with distinction. From 1996 to 1998, he was with CSELT, Turin, Italy, as a concept engineer for architectures and synchronization of data transmission networks. From 1998 to 2015, he was with Infineon Technologies in Austria as lead principal engineer for analog mixed signal design and manager of the clock and interface systems group. From 2015 to 2018, he was with the Programmable Solution Group of Intel Corporation, San Jose, California, as analog engineering manager for the development of high-speed serial interfaces for FPGA applications. Since 2018, he has been with AMD in Santa Clara, California, as Silicon Design Engineering Director, focusing on high-speed wireline transceivers. Dr. Da Dalt served on the Wireline Subcommittee of the ISSCC from 2011 to 2015. He is the recipient of the 2010 IEEE Transactions on Circuit and Systems Guillemin-Cauer Best Paper Award for his pioneering work on digital bang-bang PLLs, and the recipient of the 2017 ISSCC Outstanding Forum Speaker Award. He is co-author of the book Understanding Jitter and Phase Noise, A Circuit and Systems Perspective, Cambridge University Press. He has co-authored over 30 journal and conference papers and 12 granted patents. Please join me in welcoming Dr. Nicola Da Dalt.
Thank you, Ali. Good morning, everyone. I hope you're fine, all fine. I will be talking today about jittering wireline and data applications. I have a small issue. I don't see my slides here, so I see the slides only there. So I will have my paper copy of the slides here so to keep track. So apologize if I just every time now and then I have to turn the pages here, okay? Okay, so this is the overview of the talk. We'll start talking about jitter in data application. We'll start with the DAC, no return to zero DAC, and then followed by return to zero DACs, and then we'll follow with the Nyquist ADCs and interleave and oversample ADCs. The second part of the talk will be about wireline, jitter in the wireline applications, and we'll start with a general introduction into CDRs. And then I will spend some time talking about the jitter transfer, jitter generation, and jitter tolerance functions, which are kind of central to the, oh, thanks, Ali, which are, thank you so much, which are central to the concept of jitter in wireline. And then I will go on, I will spend some time explaining you some concepts regarding bang-bang CDRs, and then I will conclude my talk with some discussion about jitter in connection with data eyes and eye monitoring. Okay, so let's move to the next slide. Oh, wait, I have to do that myself. 1 second. Okay, so let's start with the binary DAC, no return to zero. So this is, what you see here is a basic diagram of how a current DAC is working. It's really, really simple. Basically, the IDAC converts the digital input into current output by looking at the input of the digital signal at its input, which is x of k here, and based on this, on the value of the signal x of k, it outputs a positive current pulse or a negative current pulse every time there is a rising edge of the ideal clock, ck. In the following discussion, we'll assume that the DAC is a binary, so there's only actually two values, at plus IR and minus IR. If you have a multi-level DAC, the considerations are the same, just the formulas will be a little different. I will talk about this at the end of the presentation. The problem here, okay, what is the impact of the jitter here? So the jitter on the clock CK will basically impact the output waveform and will make that will cause the impulse of currents to be displaced from their ideal position. So in the following slide, we'll try to quantify the error at the output with respect to the ideal output. So in this slide, we'll try to approach a quantitative evaluation of the error, right? So, by the way, every jitter I will be discussing about in the presentation on data converters is the absolute jitter that Ali was mentioning before, and so I will indicate it with A of k like Ali did it. So the jitter A of k on the real clock moves the edge of the input signal with respect to the ideal one, as you can see in the second. Let me see if I can do that. Oh, sorry. Okay, you can see here the clock on the jitter on the clock will move the edges of the rising of the pulses with respect to the ideal one. If you make the difference between the two, you will find that the error due to the jitter has the shape of rectangular pulses in correspondence with the transitions of the output pulse of the currents. So at the end, actually, you can represent the real IDAC with the jitter clock as the combination of an ideal DAC with an ideal clock plus an additional error component at the output, which has this shape here is as shown in this picture here. Note that even though the error has a shape of rectangular pulses, you can represent them also as a sequence of Dirac impulses, as you can see in the last picture on the bottom on the right-hand side, where the impulse are equal, the energy of the impulse is equal to the energy of the error, which is 2 times the amount of the output current times the jitter amplitude. Okay, so now we'll try to analyze and come to an estimation, to a formula that expresses the power of the error. So we start, we go through the formulas right now. So we start with the error sequence. The error sequence can be expressed as the multiplication of 2 times the amplitude current times delta k, where delta k is a quantity that represents whether the data has been changing between the previous sample and the next sample. So it's basically the data transition value. And the data transition value is then multiplied by the step function at 2 different times, one KTS and one KTS. Oh, sorry. Sorry. KTS and one KTS minus AK, where AK is the jitter. So if you take now the energy of the signal, the energy of the error, as you can see from the equation there, the energy of the error is equal to 4 times the energy of the pulse or of the current times the square of the data transition and times again the difference of this step function. Now to go to a more this is the time domain view of the error energy. Now to evaluate it in a more statistic way, we go first to calculate the error power over one period. To do that, you take the integral of the error squared, and you average it over one period of the clock, which is Ts. So the result is equal to basically 4 times the current squared times the data transition squared times the absolute value of the jitter divided by the period, T of S. Now, whenever we talk about jitter power, we want to understand what is the statistics of the power. So we take the averaging of the previous formula, which gives us the variance of the error. And as you can see, it's very easy to see that basically the power of the signal is equal to 4 times the current squared, the variance of the data transition, times the expectation of the absolute value of the jitter divided by the period, T of S. Now, this happens because we consider that the jitter is statistically independent from the data transition, so that basically when you take the expectation, you can factorize the expectation into different parts. So now, assuming that the input signal of the DAC is a random binary signal, it turns out that the variance of the data transition is equal to 0.5. And if you assume that the jitter, and this is just an assumption for convenience, that the jitter has a Gaussian distribution, you see that the expectation of the absolute value of the jitter is equal to the square root of 2 over pi times the standard deviation of the jitter. As Ali has shown before, of course, the jitter can have multiple different shapes and distributions. So this is just a case where the distribution is Gaussian, which is most of the case that you find in a well-behaved system. If you put all together, you will see that the power of the error at the output of the DAC is equal to the formula which is in the red frame. And one thing you should note here is that the error of the variance, so the error power is proportional to the jitter standard deviation. Okay, now let's see what happens if you have a DAC followed by a linear filter. The previous discussion was with the DAC basically almost ideal. There's nothing after that, but in all systems, of course, you have some sort of linear filter after the DAC. So what happens in this case? So in this case, we start from the expression of the error as a train of deltas, of Dirac deltas, as I was showing before, as you can see in the first equation. So it's 2 times IR times the sum of the data transitions times AK times the train of direct pulses. As you know, if you look at the picture on the right-hand side on the top, you will see that this error signal is filtered by the transfer function of the linear filter h of t, so that at the output of the filter, the error component will be the convolution of h of t time and the e of t, the error on the previous formula. So now there is a kind of little bit complications here. If you do the math by yourself, you'll find that the first formula, the error on the first formula, is actually a cyclostationary process. Cyclostationary processes are kind of difficult to analyze mathematically. So normally what we do when we have a cyclostationary process is just to averaging over one period of the clock so that it becomes stationary. So, and that's what intrinsically I'm doing here. And you see, if you do that and you calculate the power spectral density of the stationary signal corresponding to the E of t, you will find what is described now in the third formula, that this power spectral density is equal to 4 IR squared over Ts times the variance of the jitter, of the absolute jitter, times the variance of the data transition. Now you have the power spectral density of the error, and you go through a linear system. So by basic linear theory, you know that the power spectral density at the output of the filter will be given by the power spectral density of the input times the squared of the absolute of the transfer function of the filter. And this is what you see in the formula in the red frame here in the integral. That's basically the product of the spectral density of the input error times the square of the transfer function. Now, to calculate the total power, having given the power spectral density, you just have to integrate over the whole frequency range. And that's how you calculate the total error in this case. So note here that in this formula, the jitter appears as with the variance, while in the previous formula, where in absence of the linear filter, the jitter was showing as just present with the standard deviation. So there is a difference here, and I will go over it in 2 slides to understand why there is this difference. However, now let's try to apply this simple case, this formula to a simple case where which is almost probably the most common case, where the linear filter is just a normal low-pass filter of first order. So here you see that for a first order low-pass filter, the transfer function is simply a first one-pole transfer function with a corner frequency called f3 dB. So now I could go through the equations and integrate the square of this thing over the whole frequency range, but it should be common understanding or common knowledge that basically if you go through the equation, basically you'll find that it's the equivalent noise produced by this filter is equal to a brick wall filter with the cutoff frequency at pi over 2 times f3 dB. This is a so-called equivalent noise bandwidth. So basically, then, if you multiply, if you take this equivalent noise bandwidth and multiply by the variance of the power spectral density, variance of the input error, you'll see that the power of the error at the output is given by this formula here, 2 pi, and the corner frequency of your low-pass filter with respect to over the sampling frequency times the squared of the standard deviation of the jitter over the squared of the periods, and of course times the current squared. So now let me go back one step and see here so as you have noticed, we have 2 different expressions for the IDAC error. One, if we don't put any linear filter after the IDAC, the power of the error is proportional to the standard deviation of the jitter, while if you put a linear filter, the power of the error becomes proportional to the variance of the jitter. So there is something going on here. And where is this difference coming from? Well, if you look at the picture on the bottom left part of the slide, this is the error component in the case where there is no linear filter or no low-pass filter after the DAC. You see that the area of the error doubles if you double the jitter. It's just because basically the top level of the shape of the rectangular shape stays at the same level, and you just doubles the width, so the area increases two times. On the right-hand side, though, you see that if that pulse is going through a linear filter, and for instance, some kind of low-pass filter where the shape is smooth, and the width of the error is much smaller than the bandwidth, than the time constant, sorry, of the filter, you will see that the smooth error doesn't have the time to reach to the top of the curve, and once the error goes down again, the smooth error will go down again. So now, if you double the jitter in that case, you will see that you double the time where the error goes up, and you double the time where the error goes down. So basically, in this case, the error increases by 4x and not by 2x. So that explains intuitively why, if you don't have a filter, the error is proportional to, the power of the error is proportional to the standard deviation, while if you have a filter, the power of the error is proportional to the square of the standard deviation. And so I was kind of confused myself about this thing, so I did some MATLAB simulations just to understand that I was not wrong. And what you see here is basically the result of a MATLAB simulation where you see, I took basically an NRZ IDAC, and I was following by a first order low pass filter, and I was sweeping the corner frequency of the low pass filter with respect to the clock timing of the DAC, and I was reporting the error power on the y-axis. And I did this for two values of the sigma of the jitter with respect to the period of the clock, as you can see here. So for 0.1 and 0.01. So, but basically what you see here is that if the F3 dB bandwidth of your low-pass filter is very small compared to the sample frequency, then basically you have something, the error power increases linearly with F3 dB over Fs, and it matches exactly the formula that describes the error after the low-pass filter. If the corner frequency of the low-pass filter becomes very big, at some point that filter becomes almost a no filter. So basically, the low-pass filter has such a high bandwidth that it doesn't do anything. At that point, the error of the power saturates, and it asymptotically achieves the value that are given by the first formula, which is the formula with the where you don't have a linear filter. So this is just a demonstration that the formula that were shown before are correct. Okay, another case that you can have finding some application is where the DAC is followed by a circuit which integrates the charge coming from the current and dumps it after every clock cycles. It's shown here in a very simplified way as a capacitor that is charged by the current, and then there is a switch that every clock cycle, an ideal switch of course, every clock cycle will reset the current, the charge of the capacitor to 0. So this filter here, this integrate and dump filter, has a transfer function in time, which is, sorry, a impulse response in time, which is given by the picture in the top right-hand side here, where is basically a rectangular pulse of width Ts and height 1 over Ts. So now let's try to calculate the power of the error at the output of this configuration. So here what we do is, again, we start from the power spectral density of the error as you can see from this formula here. And we use the same concept as before. This is again a linear system, so the power at the output is given by the integral over the whole frequency range of the power spectral density of the input times the squared of the transfer function. Now we use, in this case, it's much more easier to convert this integral into the time domain by using the Parseval's theorem, which tells basically that that integral is equal to the integral of this power spectral density times the squared of the impulse transfer function over time. So the impulse transfer function, as you can see on the top, is just a rectangular shape. So this is very easy to find the result for, and again the power of the output of this system the error power will be 4 times IR squared times again the variance of the data transitions over sigma A times sigma A over TS squared. Okay, this, so sorry, before we go to the return to zero DAC, I want just to underline that all these formulas were done with the 2-level DACs. If you have a multi-level DAC, all the derivations that are shown here are exactly the same. The only difference is that the term sigma-delta squared, so your statistics of the data transition will change. That's the only really component that changes in all the formulas. The rest stays the same, and you can find by yourself on a multi-level DAC what is that value. It's not very difficult to find out. So what happens now if you have a return to zero IDAC instead of a no return to zero? So there are a couple of things that are different in this case. First of all, you always have 2 transitions per every DAC cycle. So there is no need to include the term delta, the delta term there, because you always have a transition, because you always return to zero, and then you either decide to go up again or down. The second difference is that the magnitude of the error waveform is 1 IR instead of 2 times IR. But for the rest, basically, the derivation of the formulas for error just follows the same outline that we discussed before. So if you do it by yourself, you'll find that basically the result for this kind of return to zero IDAC are identical as the result for the return to zero DAC, except that you have to replace the value sigma A with the sum of the sigma A and sigma B, where in this case we denoted with A of k the jitter on the rising edge of the DAC and B of k the jitter on the falling edge of the DAC. But basically, if you just apply this simple replace this, the variance with the simple formulas here, basically you will see that the formulas are the same. Of course, the SNR of the DAC depends in this case on the on time of the return to zero pulses with respect to the period TS, which was not the case in the no return to zero, because the pulses always had the same width as the period. Okay, this closes the section about the IDAC, and the next one I will talk about is we'll talk about the Nyquist ADCs. So Nyquist ADCs basically include flash ADCs or successive approximations ADCs, SARs, and even pipeline. So the concept of Nyquist ADC is very simple. You have a continuous signal x of t, which is sampled at a constant time interval t of s. The sample signal is quantized by the ADC on n bits, and okay, even without considering jitter, of course, on the first place, just due to the limited resolution of the ADC, the output signal carries a so-called quantization error. This is very much known. And if you assume that the quantization error has a wide spectrum, then you find and you work through the math, you find that the signal to quantization noise ratio, SQNR, is basically given by 6 times the number of bits plus 1.76 in dB. So every bit you add to the ADC, you gain 6 dB of SNR. This is a very classic formula, so there's nothing special in that. This assumes that the clocking the ADC is perfectly ideal. So what happens if the clock is not ideal? You will be sampling the jitter not at exactly the time you want to sample, but a little bit earlier or later, depending on jitter, right? So for the to simplify the treatment of this kind of problem, it's useful to think of the Nyquist ADC as composed of 2 different blocks. The first one is just a pure sampler, which is taking your analog signal, generating another analog signal, which is the sampled version of the first one at exactly the rising edges of the jittered clock. This signal S of t is then going through the quantizer and then is quantized to give the output of the ADC. In a simple model, the timing error and the quantization error can be linearly added. This is not always the case. If you think really more carefully through the whole system, you will see that they do actually interact, but for a first order approximation, we'll assume that timing error and quantization error are just added separately to the final error. So in typical designs also, in typical ADC designs, normally you want to make the timing error negligible with respect to the quantization error. So now, in the following slides, we will focus exclusively on the timing error. We will assume that for now the quantization error is at 0. So, this slide is basically fundamental to understand the sampling error in ADCs. So on the picture on the left-hand side, you see just a voltage waveform, continuous voltage waveform, which you want to sample at the instant KTS. Due to jitter, though, you are not sampling at KTS, you're sampling a little bit far, AK, where your absolute jitter is AK, far from the KTS. So as a result, your sample signal will not be the one that you wanted, it will be a different one, and you will get an error A of K. So now, if we assume that the analog signal is well behaved, so meaning it's kind of a smooth signal, and assume that the jitter is small compared to the period of the clocking of the sampling clock, you can expand the analog signal via a Taylor expansion, as you see in the first formula on the right-hand side on top. So your output signal will be equal to the signal at exactly the time that you wanted to sample, KTS, plus an error term. And the error term is basically the derivatives of the signal at that exact time the amplitude of the jitter A of K. Of course, a Taylor expansion would include also higher order terms, but under the assumption that the jitter is very small, you can just close it at the first term. So analyzing this first formula, you will see that the error component, which is your the difference between y of k and x of KTS, is actually nothing else than the product of the derivative of the signal at the sampling point times the amplitude of the jitter. So at the end, the error in this kind of sampling process is proportional to the slope and proportional to the timing jitter. So let's try to apply this easy formula to one of the most widespread cases where you assume your signal, input signal is a sinusoidal with a given amplitude A. You calculate your derivative x prime, it's A omega times the cosinus. So now applying the formula before, the error is the product of the derivative times the amplitude of the jitter. So, and then we want to calculate the power. So the power turns out to be equal to the A squared omega squared times the expectation of the product of the cosinus times the amplitude of the jitter squared. So you can factorize those because basically they are kind of independent. So the first expectation of the cosinus squared is 1/2, and the second factor there is the variance of the jitter, sigma squared of A. So now, if you want to calculate the SNR, you just have to take the power of the signal, which is, for a sinusoidal, is A squared over 2, and divide it by the power of error that we calculated just before. At the end, you find that if you express everything in dB, the SNR is equal to 20 log 10 of 1 over 2 pi f over sigma A. So basically, it's inversely proportional to the frequency of the signal and inversely proportional to the standard deviation of the jitter. This is a very, a well-known formula, but I think it's good to know where it comes from and what are the approximations, assumptions that lie below in this formula. So if you plot this formula over for a few cases, you will see a graph like this, where on the y-axis you have your signal frequency, in this case is represented in megahertz, and on the y-axis you have your SNR in dB. And depending on the sigma A, on the standard deviation of the jitter, you have different curves. This curve tells you basically for a given analog signal frequency, and for a given SNR, which is your target, what is the jitter that you can maximally tolerate? For instance, if you look at this simple case, it's easy maybe to remember. If you have a 10-bit ADC, your SNR, target SNR is around 62 dB, and your signal, input signal is at 10 megahertz, you will see that from the curve here and from the red dot, you see that if you have a 10 picoseconds RMS jitter, it basically, it will give you exactly the 10 dB. So basically, just because of the timing error, you will have SNR of 60 dB. So of course, if you want this to be negligible with respect to your quantization, you will have a jitter, you will need to have a jitter which is way below 10 picoseconds. If you look more in details in this graph, you see that, for instance, if you have a very high frequency signal, like something around 1 gigahertz, and you want a 10-bit ADC, which is pretty challenging at that point, you will see that the amount of jitter that you are allowed to have is on the range of the 100 femtosecond. So we did the case of a sinusoidal signal, but what if you don't have a sinusoidal signal? Normally, I mean, in a system you have a generic signal coming from somewhere else, so it's not always sinusoidal. So if you go through the references at the end of the paper, you'll find a couple of them that handles this case, and basically, you see that the power of the error is equal to the product of the second derivative of the signal autocorrelation at 0 and the variance of the jitter. So big R of X is the autocorrelation of the signal, and the 2 primes means the second derivative at 0. So where does this formula come from? So let me go back a couple of slides And actually, it basically you can derive this formula directly from the formula of the error term here. If you take the variance of this guy, you will have, and you can factorize in the product of the variance of the jitter times the variance of the slope, you will find that the variance of the slope is actually nothing else than the second derivative of the autocorrelation. So it's not a very complicated thing. It's just maybe the way it's shown lets you makes you understand it's complicated, but it's not. So let me go back. So so what does this formula tells us? First of all, what is the autocorrelation of a signal? So the autocorrelation, in very simple terms, is a measure of the variability of the signal over time. So the more the signal changes over time, the more the autocorrelation drops to zero fast, right? If you have a constant signal, the autocorrelation is a constant. If you have a white noise, meaning that the signal changes very fast, the autocorrelation is just a delta. So in reality, you have something in between. And you can see here down in the bottom pictures and examples of, just pictorially represented two waveforms. One changes, the solid one changes more slowly than the other one. And if you plot the autocorrelation of the two, you will see that the autocorrelation of the solid one has a smoother curve, and the derivative of that autocorrelation at zero is basically smaller than the derivative of the second one of the curve that has faster changing. So basically that's the physical meaning of the formula in the frame, in red frame here. Also notice that the error power does not really depend on the shape of the power spectral density of the jitter, it just depends on the total power. This is because the autocorrelation there in that formula comes with the, it's only evaluated at zero, which is the integral of the total power spectral density. Okay, now we have seen in what happens with Nyquist ADCs, and again, those formulas applies basically to flash ADCs, SARs, and pipelines. Now, recently there have been a lot of activity around so-called time-interleaved ADC. Time-interleaved ADCs are used in very high-speed applications where you have to sample very high-speed signals, multiple of several gigahertz. And if you make an ADC, if you want to build an ADC that is able to go at that amount of gigasample per second, you will spend a lot of power and a lot of energy. So the recent state of the art is basically use multiple sub-ADCs. Each of them is sampled at a much smaller frequency, and then you max the output of these ADCs and you create one bit stream at a much higher frequency. In this case, in the picture, I showed like 4 sub-ADCs. Each of them is clocked by a different phase of the same clock. So you create one clock, CK, which has 4 phases, equidistant from each other, and you use each of the phases to clock one of the ADCs. So if each subsample ADC is sampled at frequency fs, then the output of the n ADCs combined and the total aggregate equivalent sample rate will be n times fs. So basically, the trick here is really to use multi-phase clock at the same frequency spaced uniformly over one clock period. So now let's see what happens in terms of what are the errors that non-idealities that can occur in this kind of ADCs. So there are several things that impact the performance. Like you have each ADC might have a different offset, so you have offset mismatch, you have gain mismatch of the different ADCs. Of course, you have jitter on the clock, as we observed before and described before, but there's one more component here which is not present when you have a single ADC, and that is the timing skew among the clock phases. So ideally, you would have all the phases equidistant, but due to the way that you build a circuit and you lay out the circuit, there are always a difference in the delay between the place where the clock phases are generated and when they get to the ADC. So you have differential delays between the phases, what we call timing skew. So we called this, in the formulas that will follow, we'll call this timing skew, indicate this timing skew with a tau 0, tau n minus 1. And since these deviations are constant in time, we don't call them jitter, they are deterministic, so that's why the term skew. But we will see that, we work through the formulas now, we'll see that their effect is actually equivalent to a high frequency jitter. So this formula is a little bit, this slide is a little bit dense, so I will try to explain you in high level what is happening here. So basically, if you go through the, and there is reference in the back, so each phase sample the analog input signal at different times. So if you have a skew, like in the previous case, 4 phases with each of different skew, after 4 samples, the first phase will come there again, and the cycle will repeat every four samples. So basically, you have an error which repeats itself every n cycles in an identical way. And again, this is again a cyclostationary process. So the mathematical treatment is again a little bit more complicated, and I'm not going to do it here, but there is a reference or 2 references at the end of the presentation. And you go there, you work through the equations, you'll find that the SNR at the output of the ADC has this somehow complicated formula here, where the numerator is actually nothing else than the power of the signals, but the denominator is pretty convoluted. There is 2 times the power of the signals minus the average over the number of ADCs of the autocorrelation of the signals skewed by the measured at the skew of each phase with respect to the average of the phases itself. So a tau of hat is basically the average of the skew, and tau k minus tau hat is the deviation of the skew of each phase clock with respect to their average. So, okay, this is quite complicated, and it was difficult for me to understand actually what does this actually mean. So what I tried to do is to get a more intuitive or more simplified version of the formula. So I tried to do, okay, let's try again to simplify the expression by taking the Taylor expansion of the autocorrelation at tau k minus tau hat. And again, if you assume that tau k minus tau hat is very small, meaning the skews between the signal is kind of small, again, you can expand around 0, and you'll find the second formula in the formula, the 3rd bullet there, which I expanded till the 2nd term, and I neglected the terms of higher order. So now, if you assume that the slope, sorry, the first derivative of the autocorrelation at 0 is 0, which is mostly valid for all practical real signals, and you plug this formula, the second formula, into the first one, you see that the formula simplifies to what is reported on the bottom, which is on the numerator the power of the signal. In the denominator you find the second derivative of the autocorrelation at 0 times an average of the sum of the skews of each phase with respect to their average value. And that sum, 1 over n times the sum of that term, is nothing else than, if you want, the variance, the sample variance of the skew. So basically, at the end, you find the last formula here, which is exactly the formula that we found a couple of slides ago that tells you that the error of the power is proportional to the second derivative of the autocorrelation times the variance of the jitter. So basically, it's identical in the form to the SNR for a Nyquist ADC. So basically, it tells you, even though the skews are not really a random phenomenon, but at the end, you can apply the same formula, calculate the skew variance, and you will be able to calculate your SNR like this. So, however, there is a big difference between this kind of skew, timing skew, and the random jitter. So, timing skew are deterministic, so they never change in time. So, you could think of correcting them. You could think of compensating the delays between the phases so to make this 0. And indeed, there have been papers published recently that try to do that. There are basically, as far as I know, there are basically two approaches to try to compensate the skew or to eliminate the error due to the skew. And one is by using post-ADC DSPs, and the other is by detecting somehow the skew with some digital post-processing and then correcting the delays of the phases and try to minimize the skews. So in the reference that you see here, the authors used adaptive filters after each of the ADCs to try to estimate the timing error, and I'm not going to go through that. The mathematics there is quite complicated, but basically doing some clever algorithms, they were able to detect how much is the skew of each of the phases, and then by multiplying the skew by the slope of the signal that they detected because they had multiple ADCs, they were able to calculate the error and subtract this error from the output of the ADC. So again, here they just didn't do any attempt to correct the skew of the phases, they just corrected in the error with a post-processing. However, I mean, adaptive filtering and DSP are normally a power-hungry approach, so this will increase the total power of your ADC, so it's not always the most desirable thing to do. So the other approach was, or is, to try to detect the skew and then, with a feedback loop, adjust the phases of each of the ADCs, as you can see in the picture here. There's one example shown in a paper at ISSCC 2013. You can see in the bottom picture on the right. So here the basic concept is, so this is applied to a wireline system. There was a 10 gigabit per second signal sampled with four sub ADCs. And since after the ADC, the signal is a digital form, you can think of doing a lot of post-processing in terms of equalizing the signal. In this case, the authors put a so-called FFE, feed-forward equalizers, which is nothing else than a FIR filter, to equalize for the channel before the decision feedback equalizer. So now, since the channel is the same for all ADCs and the ADC should be identical, the optimal coefficients that equalizes the signal should be identical between the four ADCs. And the author, after correcting the offset of the ADC and the gain, any other mismatch between the FFE coefficients must have been due to the skew of the phases. the authors use this information to feed back to the phases and correct the skew so as to minimize the difference between the FFE coefficients of the different channels, and thus effectively reducing or eliminating the skews between the signals. Anyway, so this is kind of a very advanced thing, and you have the reference there if you want to go read, but it's definitely, I mean, talking about this would take 1 hour by itself, so I'm just going very fast over that. Okay, what other kind of ADC do we have? So the last kind of ADC I want to talk about is Sigma-Delta ADCs. There are really 2 types of Sigma-Delta ADCs. There is a continuous time and there is a discrete time. Let's start with the continuous time Sigma-Delta ADCs, which is the first order, the very simple first order Sigma-Delta ADC is shown in the picture here. You have an input signal, and then you have a feedback signal from a DAC. They are subtracted, the result is integrated, go through a quantizer, and the quantization, the quantized values then feed back through the DAC to the input again. So, so the impact of the jitter in this kind of Sigma-Delta ADCs is basically twofold. First of all, it's, there are 2 clocks. There is the clock that drives the quantization, and is the clock that drives the DAC. So these are the 2 points where jitter is injected. To understand how the jitter affects the SNR of this kind of ADCs, it's useful to see it in terms of the 2 main transfer functions. One is the so-called STF, the signal transfer function, which is the transfer function from the input to the output of the Sigma-Delta ADC. And the second is the noise transfer function, which is the transfer function from the quantization output to the, from the output of the quantizer to the output of the ADC. So, so now we use a simplified, view of the ADC, and we'll assume that the effect of the jitter on the quantizer can be represented as a noise injected at the output of the quantizer, and similarly for the DAC, the error due to the jitter can be added linearly at the output of the DAC. So you can see that the quantization noise of the quantizer is filtered, is transferred to the output of the ADC via the noise transfer function. While the DAC error is on the feedback path, but basically from a linear system is equivalent to a noise at the input, so it's transferred to the output of the ADC via the signal transfer function. So if you use a superposition, the total power spectral density at the output of the ADC is given by the Ph.D. of the quantization noise times the noise transfer function squared plus the DAC, the Ph.D. of the error of the DAC times the signal transfer function squared. So and basically using this formula, you can calculate the output of the, the error at the output of the ADCs. In the previous slides, we saw how to calculate the power of the error of the DAC and the power of the quantizer. So you have all the information needed to calculate the error at the output of the ADC. But I want to show you, I want to highlight one important thing, and that for how a Sigma-Delta ADC works, the signal transfer function, so the transfer function from the input to the output, is basically equal to 1. That's how there's a very the very essence of the ADC. But the noise transfer function for a sigma delta is shaped, is frequency shaped. It's basically very small for in-band, till you are in-band of the signal, and then it grows depending on the order of the filter. Basically, we use oversampling here to reduce the quantization noise of the in-band. So, given the formula, you see that the the signal transfer function for the in-band is much bigger than the noise transfer function in the in-band for the frequency which are within the band. So if you see this and if you relate to the formula before, you will see that the output is in a Sigma-Delta continuous time Sigma-Delta ADC is typically dominated by the DAC error. And again, the noise, the error due to the jitter on the quantizer basically is filtered by the high pass of the Sigma-Delta, so you don't have it at the output. So design of the DAC in Sigma-Delta ADC is pretty critical for jitter. So now we'll move to the second kind of Sigma-Delta ADCs. These are so-called discrete time. In this discrete time ADCs, the sampling occurs at the input of the modulator, as you can see in the picture on the top right. This is followed by the loop filter, by quantizer, and by the DAC on the feedback, as in the example before. But in this case, normally discrete time Sigma-Deltas are implemented using switch caps. So for instance, in this case, which is a simple first order Sigma-Delta, the loop filter, the input sampling plus the loop filter plus the feedback from the DAC is implemented like in the picture in the bottom right. So now, even though Sigma-Delta ADCs, continuous time or discrete time, are similar in terms of how they treat the signal, but they are very different in terms of how jitter impacts them. So for discrete time Sigma-Delta ADCs, there are basically three main points where jitter is injected. The first, denoted here by the number 1, is the input sampling. So basically here you're sampling the input signal, so all the considerations that we did for Nyquist ADCs are valid. And also here the transfer function from this point to the output is equal to 1. So basically all the noise all the error that you generate here is transferred to the output 1 to 1. So the second, and this is basically one main component. The second component is, again, the error from the DAC. But since this is a sampled system, if the timing is designed appropriately, the timing constant of the DAC is much faster than your sampling period. Whenever you sample, the DAC output is already at level, so you are not really sensitive to whether to the rising edge of the DAC. So the component number 2 is really normally very, very minimum as long as the feedback timing is closed properly. The third component is, which is intrinsic in Sigma-Delta ADCs, is the charge transfer from the capacitor C1 to capacitor C2. Again, here, if the design is done properly and there is enough time constants for C2 to charge properly, every jitter that you have on the phase 2, Phi2, is not going to impact your charge transfer significantly. So again, also this kind of impact is very minimum. So basically in Delta Sigma ADCs, the main component is really the first one, the sampling of the input signal, again, where all the formulas that we derived for Nyquist ADC can be applied. Okay, how are we doing for time? 20 minutes. Okay, this concludes the ADC and part of regarding ADC. Now I will go through the jitter in the wireline applications. So this diagram shows you a simplified CDR-based wireline system. I think we saw this picture already in the presentation of Ali before. I'm not going to spend too much time, but basically at the transmitter, the digital data are clocked and transmitted over a lossy channel. On the RX side, you have an equalizer that compensates for the channel losses, and you have a clock and data recovery that has two functions. First, recovers the clock, and secondly, samples the incoming data and delivers them to the digital domain. So jitter, in this case, jitter on both the TX and the RX limits the BER, the bit error rate. So I will give you first a very first high-level view of the formula for the BER. Let's assume that there is no jitter on the TX, that there is no the channel has ideal bandwidth. So basically, the data that you get at the input of the receiver are ideal rectangular shaped signals. And we assume that the receiver clock jitter is Gaussian and uncorrelated with the data. So as you can see from the picture here, as long as you are within the window, the valid data window of the data, you will not have an error. But as soon as your jitter moves the clock edge outside of the data, you will get an error, right? And if you can see in the second picture below where you show the Gaussians, the probability of error is determined by the probability of finding your clock edge outside of the data edges. If you work through the equations, you see that the probability of error is basically given by the error functions of q over square root of 2, where q is the ratio of the half UI over your over the standard deviation of your jitter. On the figure on the right-hand side, you see that formula shown for different values of Q and different values of the probability of error. So, for instance, if you want a probability of error of 10 to the minus 12, then your sigma, the sigma of your jitter, should be such that 7 times that value is lower than 0.5 UI. So anyway, in real systems, jitter is present on the data edges due to the clock on the TX. The channels at inter-symbol interference, closing the eye both horizontally and vertically. Then on the receiver path, you have voltage noise, you have offset, and all these components closes your eye even further. And last but not least, the clock on the RX is, since it's derived, extracted from the data through the CDR, is correlated with your data jitter. So this makes all the equation, all the consideration a little bit more complicated than what I showed before. So this is a diagram that shows you in a very high level what is, how does a CDR work. In this case, it's an analog CDR with a charge from a loop filter. You have a phase detector which has two functions. It detects the phase error between the data and the clock, and also it uses one of the clocks that from the VCO to sample the data in the middle of the eye. The charge band loop filter integrates the phase error and generates a signal through the loop filter, a signal to control the VCO. And the VCO, of course, generates the clock, which is used to sample the phase detector. So it's basically very similar to a PLL loop. The main difference is that the input is not a reference clock, it's data. So there might be, so data is not always 010101, you have missing transition. So the phase detector there is a little bit different. I will show you later. So how to analyze the CDR? So the best way of analyzing this is by linearization. If you linearize all the blocks, you will see that the phase detector plus the charge band can be condensated is just one constant called KPD, it's just a proportional constant. The loop filter has its own transfer function. The VCO is a classical integrator. So normally when you analyze CDRs, there are two functions that are most important. One is called the jitter transfer function, and the other is the jitter generation. Jitter transfer, H of t, describes the jitter at the CDR output due to the jitter on the data input, while the jitter generation is basically the transfer function of the VCO noise to the output. And the total jitter is the superposition of the two components. And as you can see for the formulas via linear superposition. Now, let's make an example here of having a very simple loop filter, which is actually, or even the most used, is just an RC. You don't really need more than that for a CDR. We assume here that, again, that the phase detector can be modeled as a linear gain. So in this case, the transfer function, the jitter transfer function has 1, 0, and 2 poles, and has a low pass characteristic as described by this formula, and basically is a 1, 0, 2 pole system. So how does this formula look like in the frequency domain? Well, the shape of the transfer function really depends on the damping factor psi. It has, of course, a low pass characteristic. So basically, it means that the CDR tracks the low frequency jitter on the data, but it does not track the high frequency jitter. So if you consider that the output of the CDR is fed back to the phase detector, you will understand that as long as the jitter on the data is very low frequency, your CDR is able to track it very accurately, so you won't have big problems. But as soon as the jitter on the data is very fast, above the bandwidth of your CDR, your clock of the from the VCO will not track anymore, will just stay where it is. So you will have a lot of relative jitter between the data, which are moving fast, and your clock, which is basically fixed. So, and that's what Ali was referring before with relative jitter between data and clock. So in this case, the BR is likely really to be limited by high frequency jitter on the data. So, have you seen from the formula before, you've seen that we have a 0 in the transfer function. So what is the effect of that 0? But in the transfer function, the effect of that 0 is just causes some peaking on the jitter transfer function, as you can see in this picture here. And really the peaking depends on the damping factor. So what does that peaking mean? It means that if you have a jitter component around, with a frequency around that peaking value, the output jitter is bigger than the input jitter. So you are basically amplifying your jitter at around that frequency. So is this a problem or is not a problem? It depends on your application. In some cases, well, in general, if the peaking is high, it's always a problem. But there are applications which are really, really sensitive, even to minimum amount of peaking. And this is the case when you have repeater chains, when you have basically blocks which are cascaded to each other. Each block is a receiver of the data and uses the same recover clock to transmit the data to the next block. And you can think of this as like when you have geographical communication networks very kilometers apart, or even hundreds of kilometers, you have repeaters to keep the signals going. And you can have many of them in series, right? So if each of them amplifies the jitter at a specific frequency, after the chain of repeaters, you really have a lot of jitter at a specific frequency, which basically reduces your BR. So the bottom line is, if you have this kind of application, you have to be very, very careful about sizing the CDR so you don't have too big of a peaking. And I think it's really measured in some cases for certain standards, even in milli-dB. So it's really very, very critical. So here, this this slide shows you the basic of the poles and zero, how they move when you change the gain of the system. And it shows you that to reduce your peaking, basically you have to make the gain of the system high enough so that one of the poles moves as close to the zero as possible as to cancel it. It's just classical, you know, root locus theory, nothing more than that. Okay, what about jitter generation? So again, jitter generation is the transfer function from the VCO to the output. So for a very simple system like we showed before, the jitter generation function is a high pass with a 2-pole and 2 zeros at the origin. But you will see that the jitter generation has the same, the poles are the same as in the jitter transfer. And the 3 dB corner of the two are the same. So the jitter transfer is a low pass, the jitter generation is a high pass, but the 3 dB frequency is the same. So what does it mean? It means that in this kind of topology, they are connected. You cannot move one without moving the other. And this is not always desirable because you would like to have the jitter transfer having a lower corner frequency as possible. But by doing that, your corner frequency for the generation decreases as well. And this, if you know a linear system, this will tell you that you have much more of the noise of the VCO going to the output. Especially in CDRs, you normally use ring oscillators because they have a wider tuning range. You don't use LC. So phase noise is a real concern there, especially the flicker part. If the frequency goes too low, then you get too much noise of the flicker, and that degrades your system. So for this topology, jitter transfer and jitter generation cannot be optimized independently. But there are topologies in the literature which try to decouple the two things, and you can see them in the references. Okay, one more central concept when we are talking about CDR is the jitter tolerance. Ali was telling you in the previous presentation that when he was talking about sinusoidal jitter, this is used to test the robustness of a CDR. So how does this work? Basically, you generate PRBS data, and you feed this data to the CDR, and then after the CDR, you extract the data and you measure the bit error rate because you knew the PRBS pattern, so you can see if the data that you receive are correct or not. So in this test, though, the PRBS generator is clocked by a clock which is modulated in a sinusoidal way, and the frequency modulation has a given amplitude, phase modulation has a given amplitude and a given modulation frequency, AM and FM. So what we do is basically sweeping the frequency, the modulation frequency from very low frequency up to maybe 100 megahertz and so. And for each of the modulation frequencies, you increase the amplitude of the modulation itself till you start detecting BARs at the end of the, after the bit error rate tester. So then you plot this curve, you plot the curve that shows you at what point you start seeing BRs, and you get a curve as shown in the picture on the top right, which is basically for very high frequency, it has a flat asymptote, which is below 1 UI. But if you go at very low modulation frequencies, the CDR being able to track those modulation can tolerate higher amplitudes, and so you see that the curve goes up with like a f squared. So how does this, where does this shape come from, right? So next couple of slides, I'm trying to explain you where this is, how to derive this form, this shape. So assume first of all that, again, going back to a very idealized system, you have no jitter and perfect equalization, so your data is basically a full 1 UI pulse. So in these cases, you get an error only if your phase error of the receiver clock is such that your edge is falling outside of the 1 UI window. So the question that we ask ourselves is, for a given modulation frequency, what is the minimum amplitude of your modulation that causes the phase error of the recover clock to be larger than 1 UI peak to peak? If we answer this question, then we'll find out the equation for the jitter tolerance. So, so now to get there, we define first each of V as the transfer function from the input of the CDR to the phase detector error, phase detector output, so which is the point after the summing point there. And this is really the ratio of the phase error over the phase of the input. Phase of the error versus the phase of the input. Then, if you turn around the formula, you see that for a given error phase, the corresponding phase of the input is given by 1 over this error transfer function times the phase of the error. So now we impose the phase of the error to be 1 UI. That's our criteria for being at the edge of having some error. So the input phase corresponding to this will be the JTOL, the jitter tolerance, and it turns out to be basically equal to the absolute value of 1 over that specific error transfer function. So what is that error transfer function? This is then again the linear system. You work out, it's basically 1 minus the h of t of s, the jitter transfer function. So in a very simple system we were analyzing before, the jitter tolerance has then this expression here, and you will see that for very large frequencies, the jitter tolerance basically equals to 1. So you have 1 UI over JTOL, while for very low frequencies, it grows like 1 over f squared. Note that if you have a if your CDR loop is not well damped, so the damping factor is not high enough, around your natural frequency, you will have a dip. So the jitter transfer function will decrease. So exactly at that point, your CDR will have its weakest point in terms of being able to tolerate input jitter. So there is another second order effect probably if you have that comes into play with the JTOL here. And if your VCO tuning range is limited, there is a second limitation to that slope on the lower frequency range. So consider that your VCO frequency, your VCO can cover the frequency only from the nominal plus minus delta FP. Now, if you write the sinusoidal phase modulation as the second formula there, and you take the derivative of that, you will see that the instantaneous frequency, which is coming of the data coming in, is equal to the nominal frequency plus AM times FM times the cosinus. So in order for the CDR to be able to track that kind of data deviation, the VCO has to be able to generate this frequency. So if AM times FM is bigger than your delta FP, then the VCO cannot track, and basically will get errors. So this this brings another limitation to the maximum amplitude, which is given by the last formula in this slide. But normally, this is really just in extreme cases relevant, because normally the modulation frequency, especially at that range, is very low, maybe in the range of some megahertz, while the delta FP is normally, at least for real CDRs with ring oscillators, is easily in the range of gigahertz. So that limit is really very high. Okay, So what are other limitations that come into play for the jitter tolerance? So we are considering ideal data, basically one UI width and no limitation on the horizontal. In practice, you have a whole bunch of other factors that closes the eye and contribute to deteriorate the JTOL. You have, of course, the jitter on the edges, both on the TX and on the RX, of course. You have interceivable interference, which closes the eye further. You have crosstalk from neighboring channels that, interferes with your channels and closes the eye even more. You have voltage noise of the transmitter, of the equalization of the receiver, and so on. You have offset. So basically, at the end, your ideal eye, once you get through all these things, is really very close, horizontally, right? So, and you cannot do better than that. So your JTOL cannot be higher than that aperture of your eye. So at the end of the day, in practice, a real JTOL curve is way below the 1 UI at high frequency. Some standards require it to be higher than 0.1. That's good enough. And normally you have also that dip there that because of your CDR damping factor. So the derivation that we did before was in the ideal JTOL, just to let you understand the shape, where it comes. But in real cases, that curve is shifted down by quite some amount. Okay, I have a couple of minutes probably to spend on the bang-bang phase detector. We were talking about the phase detector for the CDRs. The most widely spread use of the most widely used detector is so-called bang-bang or Alexander or early late. Basically, this phase detector uses two phases of the clock to sample the data at the middle of the eye and at the edges. And based on the values that it captures, and it determines whether the clock which is sampling the edge is coming too early or too late with respect to the edge. So it's a simple system, and based on a lookup table, you can detect if you are too early or too late, and then either increase the voltage of your VCO or decrease the voltage of your VCO. So that's not a big deal, but the problem here is that at least ideally, the bang-bang phase detector has a nonlinear characteristic. So you can represent it really as a flop. You have your data input and you have clock and you sample the data. So if you have really no jitter on the data, no jitter on the clock, your transfer function is basically a step. The gain of this guy is of course infinite. So all the formulas that we used before cannot be used. It's not a real case. So what is the trick here? So the trick is that in reality you have jitter, and you have jitter on the data and you have jitter on the clock, and this helps you linearize the gain of your phase detector. The key point here is that this is valid if the dynamic of the CDR is much slower than the data or the clock rates. So you can consider, for instance, as you can see here, the instantaneous phase of their sampling clock is, let's say, too early with respect to the edge. So, but due to the jitter, sometimes it samples on the left-hand side, sometimes it samples on the right-hand side. When it samples on the left-hand side, it tells you, oh, I'm early. When it samples on the right, it tells I'm late, and then it corrects the CDR correspondingly. But the correction is very slow. So that arrow there is moving to the real edge very slow with respect to the data rate. So you can use to average the output of the phase detector over many cycles. And if you do that, you will find out that the real effective transfer function of the bang-bang phase detector is actually not a step function anymore, is a smooth curve, and the slope of that curve is directly determined by the jitter on your clock. And actually, it turns out that for a Gaussian jitter, the gain of the phase detector is inversely proportional to the standard deviation of the jitter. So this is a very important concept. So in band-band CDRs, the dynamic of the loop, so the bandwidth of your CDR depends on the jitter of your data, or actually on the relative jitter between your data and the recovered clock. That's what this sigma is about. So as a consequence, for instance, of course, you know that just in normal PLL, when you change gain of your loop, your bandwidth of the system changes, and also the phase margin might change. Like in this case, even if you have just a simple RC filter, and in theory you wouldn't like to have a second pole, you have always a capacitive node before the VCO. This introduces a high frequency pole and makes your system potentially unstable if you are not taking into account, if you're not designing it properly and constraining the bandwidth variation. So really having a phase detector that changes the gain with the jitter can vary your phase margin, in some cases bringing your CDR to the edge of instability. So it's something you have to consider. Kind of rushing through here. I think we have lunch in 15 minutes. Okay. I've analyzed here only one kind of bang-bang CDR, which is the one with the charge-on loop filter and the RC. In reality, in modern CDRs, you find also other implementations, like the one which are the second, what I call B here, is a bang-bang phase detector followed by a digital loop filter with proportional integral path and followed by the DCO, which is a digital control oscillator. Or you can have a third variant where you have the digital loop filter and the DCO is replaced by an accumulator and a phase interpolator. So all these are, from a system perspective, all these are identical. You can describe all these things with the same transfer function. But of course, the designs is very different from each of those. But anyway, the concept that I was talking about in the previous pages apply to all of them. So one thing that we have to, so people recognize the problem of having CDR bandwidth depending on parameters of the jitter and so on. And actually, there were a few papers in the last years that trying to address this. The paper I'm showing here is actually published by Ali here in ISSCC 2017. What is done here is that the instability in the CDR loop has a consequence of having ringing at the output. If you take the autocorrelation of the output of the bang-bang phase detector, you will see that it has not a smooth behavior, but it goes basically kind of ringing. So they designed a system which is shown in this slide here, by which they take the output of the bang-bang phase detector, they calculate the measure, the autocorrelation, and then they find whether the autocorrelation has those under swing there, and if they detect something like this, they deduce that the dynamic of the CDR is not correct, and then they change the coefficients of the digital loop filter to bring the CDR back to a good stability point. And you can see the result on the right-hand side here, where the J-tol curves are shown with and without the adaptation, and you can see definitely the great improvement that you have if you apply this kind of systems here. I have a few slides here detailing the jitter in the received die, but since Ali was going over them before, I just skip them. the last point I want to discuss with you or show you is the so-called on-chip eye monitoring. It has different names in different companies, depending where you work. Basically, the concept is always the same. You have your normal Rx path, but then you create a parallel Rx path, and in the parallel Rx path, you start changing the time and the amplitude in which you sample your signal, and then you compare this with the signal coming out from the real Rx path, and if the two values coincide, then you'll see, okay, I'm still within the eye. If you detect an error, it means you are starting to go on the eye boundaries. So by sweeping horizontally and vertically, you can generate contours of probability that shows you basically how your eye looks like internally in your system. Of course, there's a lot of post-processing of the data there, but this can be done very slowly. The eye is a static, is a stationary signal, so you have more time to understand the statistics and all this. Actually, this system can also be used to improve your BR. And basically, the basic idea is, okay, what you see on the bottom left picture, let's say your CDR naturally or by default samples the eye in that specific dot over there. Now you can use your eye monitoring to explore in each of Y and X direction how much is the margin from that specific sampling point to the border of your eye. And if you find that you are off-center, you can basically move the sampling point both horizontally and vertically to bring your sampling point exactly in a more centered position with respect to the eye, and thus increasing or improving your BR over time. Of course, this requires some slow adaptation, but normally in some cases, some applications, this is definitely a possibility that you can do. Okay, I think this concludes my talk for today. Sorry if I went long, and sorry for the bumpy start. I'm not used to have no slides here, so it was a little bit complicated for me. Sorry for that. So this is the list of references that you have. Again, most of the material, if not, I think all of that, except a couple of things, are taken from the book that Ali and me wrote together, and the other references are here for you to read. I think this concludes my talk. Thank you for your patience.